All right? Section 10.2, energies of solution formation. All right? So this is going to talk about how do we make a solution? What are the energy factors that are involved in this? So we know this cardinal rule of like dissolves like. Right, so oil and water don't mix. In order for two liquids to mix or be miscible, right, we have to have a polar solvent that's going to be used to dissolve polar or an ionic solute. So sodium chloride, which is ionic, will dissolve in water, which is a polar solvent. A nonpolar solvent must be used to dissolve a nonpolar solute. That's why dry cleaning chemicals are often these nonpolar solvents. So they will dissolve that stuff that water isn't going to get out, because whatever that stain is a nonpolar greasy type of stain. Soap is interesting because it has a polar end and a nonpolar end, or a hydrophobic or hydrophilic end. Those are other words that we can use to describe this kind of solubility in different polarities. So, where does this rule come from? Remember, it's just saying things with similar intermolecular forces can interact with each other. So molecules with similar magnitudes of intermolecular forces are miscible. So here are the steps that are involved. Right? So when we dissolve something, I remember I said it's like Attack of the Kindergartners, right? Where you're going to have multiple small interactions overcoming some bigger, potentially bigger interactions that are within that molecule, if it's a ionic solid or between two molecules. So what you're going to have to do is you're going to break this up into a couple of steps. So first, you separate the solvent into its individual components. So that's what we call expanding the solute. So you're going to say, okay, well, in order for this interaction to happen, I need to separate and overcome the intermolecular forces of attraction between my solute. Then you're going to break apart your solvent. Right, so I'm going to take my salt and I'm going to see how much energy it takes to separate my sodium and my chlorine. Then I'm going to see how much energy it takes to overcome the hydrogen bonding in water, for example. And then you're going to allow the solute and solvent to interact with each other. And that's where you're going to see that energy change. So you're going to, in step one, you're going to take your solute. You're going to basically break its intermolecular bonds. Step two, you're going to take your solvent, you're going to expand it, you're going to break its intermolecular bonds, and then you're going to combine them into the solution. So you've got three steps. Delta H1 is going to describe the energy involved in this part. Delta H2 is going to describe the energy involved in this part. And delta H3 is going to be this mixing step where you combine the two. Right? Steps 1 and 2 require energy, since forces have to be overcome to expand the solvent. So steps 1 and 2 are going to be endothermic. It's going to take energy to overcome those intermolecular forces. Step 3 usually is going to be exothermic. It usually releases energy. So when you take something and you mix it together, right, the water separates from the water and the solute separates from the solute, and then you combine them together, and those interactions between the solute and the solvent, energy is going to form a new interaction. When you form new bonds, energy is released. It's going to be exothermic, right? Most of the time. There are some notable exceptions, right? So usually, those instant cold packs are a notable exception, and in that case, we've got a fight between entropy, which we will talk about in our thermodynamics chapter, and enthalpy, the heat of formation. So, our enthalpy or heat of solution, the enthalpy change associated with the formation of the solution. We're going to sum up those individual steps, break up our solute, break up our solvent, combine them together. And this is going to work because enthalpy is a state function. If you guys don't remember what a state function is, go back to that part in Gen Chem. Basically, it says it doesn't matter what steps we took to get there. We just need to know where do we start and where do we finish. So we're starting with separate solvent and separate solute, and then we're going to combine them into this new solution. So if we took 20 steps to get there or 3 steps to get there, as we're only looking at our final and our initial states. Our delta H of solution may have a positive sign, energy absorbed, right, endothermic, or a negative sign, energy is released, where it's exothermic. And this is just showing that for those people who like to look at diagrams like this, right? We've got some energy that it takes for steps 1 and 2, and then some energy that is released when they are mixing and forming those new bonds, and we've got this net release of energy. It could be that you sum up H1 and H2, you break apart your solution, break apart your solvent, you recombine them, right? You allow those interactions between the solute and the solvent to happen, and it's not as much. You don't release as much energy, and so we have a net loss of energy. All right, so this would be something that would be a net endothermic reaction. Right? Our enthalpy, or heat of hydration, represents the associated enthalpy change with the dispersal of a gaseous solute in water. It combines the term for expanding the solvent and that for the solute-solvent interactions. All right. Why is sodium chloride soluble in water? Nature has a tendency towards higher probability of a mixed state. Again, we're going to talk about this in way more detail when we talk about entropy. The process is naturally run in the direction that leads to the most probable state. Right? So that's talking about our criteria for spontaneity, a reaction that is going to happen without an input in energy. The processes that require large amounts of energy tend not to occur. Right? So things that take up a lot of energy tend not to happen. Doesn't mean they don't happen. For example, when we think about keeping our body out of thermal equilibrium with the room, so room temperature is about 20 degrees C, our body temperature is about 31 degrees C, we spend a lot of energy to keep ourselves out of thermal equilibrium, because if you are at room temperature in your body, you're probably dead. Right? So dissolving 1 mole of solid sodium chloride requires a small amount of energy, and it results in the formation of a solution because of the large increase in the probability of the state when the solute and solvent are mixed. Right? So we're letting entropy do some of the work for us. So we had a nice crystal of salt before, and now that crystal of salt is no longer in the solid state. It's free to move around. It's able to distribute its energy in a lot more ways. So let's take a look at some of these interactions, right? So the little table here describing what we've got for our solvent, our solute, and our sum, where we're looking at the enthalpy of solution. So if we've got a polar solute and a polar solvent, right, our intermolecular forces between each the solvent and the solute are going to be large, which means when they come together, we're going to end up with a large negative change in enthalpy as those two things are free to interact with each other. So remember, solute, solvent together, right? And when we look at the net change, it's going to be small, and we're going to get a delta H of solution is going to be small, but we get a solution that forms. If we have a nonpolar solute and a polar solvent, the interactions between the solute are going to be small, whereas so this would be something like benzene in water, right? Where we've got something nonpolar and something polar. The solvent is going to be large. When the water is then able to interact with the benzene, or whatever this nonpolar molecule is, we've got something like hydrogen bonding, and then London forces. Our enthalpy of this combined solute solvent is going to be small. It's going to have a large positive. Delta H, no solution is going to form. Now, if we have a nonpolar solute and a polar solvent, right? So our enthalpy to split apart our solute is going to be small. The enthalpy to split apart our solvent is going to be small. So this would be like mixing benzene into gasoline, where they're both nonpolar, which means that our combined, when the benzene and the gasoline can mix together with each other, our delta H of solution is going to be small, a solution forms. If we have a polar solute and a nonpolar solvent, it's just like this case up here, but now our Ute is going to be polar, right? So it's like taking water and trying to dissolve it into benzene. You're just going to form little pockets of water in there. The interaction between one benzene molecule and another is small, which means that our enthalpy of mixing, where they're coming together, is small. And so our overall enthalpy of solution is going to be large and positive, and we've got no solution forming. Right? In the case of polar, polar, and nonpolar, nonpolar, the heat of solution is expected to be small. A solution forms because of the increase in the probability of the mixed state. In the other cases, polar, nonpolar, or nonpolar, polar, the heat of solution is expected to be large and positive. Right? So if it's positive, it's saying it's going to be endothermic. You need to put energy into that to make it happen, and that energy isn't free. So large quantity of energy is required. It acts to prevent the solution from forming. And it helps us to understand the observation that we have all seen, that like dissolves like. So let's do kind of a concept check here. Right? Can we decide whether liquid hexane or liquid methanol is going to be a more appropriate solvent for the following substances: grease, C20H40, or potassium iodide? Okay, pause the video. Think about it for a second. All right. Our hexane is a nonpolar solvent. It just has these carbon-hydrogen bonds. Hexane is going to work great to dissolve that nonpolar solute grease. Methanol has this OH group in it. It's going to make it significantly polar. It's got hydrogen bonding. It's going to serve as a better solvent for the ionic solid potassium iodide, which is going to have ion-ion forces. Let's talk about 10.3, some of the factors that affect solubility.